we're going to move specifically into energy profiles, but I want to warm up and just remember what step was the rate limiting step or the rate determining step. Well, that is always going to be the slow step. That's because each successive step depends on the products from that slow step. All right. So now reaction profiles look like this. They are the profiles I've been showing you before. You probably haven't seen one that looks like this with the two humps right there. So it is a diagram to describe the progress of an energetic pathway. So the x-axis is always the reaction coordinate, progress, time, something like that. And the y-axis is always energy or enthalpy, something like that. So example number 7 asks us to look at it in our notes. And I don't believe it's example 7. I believe it is example 19 in your notes. Apologize. An exothermic chemical reaction takes place in 2 steps. Sketch an energy profile for the reaction. Label the location of the activated complexes and intermediate. Also, label the activation energy and the enthalpy change for the reaction. So, it tells me to sketch a graph. So, the first thing to do is write my, draw my axis. All right. So now it gives me 2 important clues. It tells me that it's exothermic and that it also occurs in 2 steps. So if it's exothermic, I know that the reactants have more energy than the products, all right, because it lost energy, right? And if it takes place in 2 steps, then it's going to have 2 humps, all right, 2 camel's humps. That's the easiest way to think about that. All right, so now I need to label the location of the activated complexes. So the activated complexes are the peaks right here. You can call them complex 1 and complex 2. And the intermediate is going to be that middle portion right there. That is it's not exactly a product. It could be a product if you didn't have this activation energy. All right. But, and then I also want to label the activation energy and the enthalpy change for the reaction. So the activation energy from here to here is activation energy 1, or EA1, and activation energy here is EA2. All right. Now the enthalpy change is the change from the reactants to the products. So that's going to be that one, enthalpy change. All right. So to zoom in just a little bit more, to make it a little more easier to read, but that is basically it. That is an energy profile. That is all the labeling you would need to know off of an energy profile. Now you can see energy profiles here. Pop quiz, how many steps does this one have? It has 3, right? Because it has 3 humps, right? So now, which one is the rate limiting step? Well, the rate limiting step is going to be the highest amount of activation energy is going to have the rate limiting step. So this one right here, in this one, the second step is the rate limiting step because that has the highest jump. Okay. So let's shift gears just a little bit into reaction rates and see what it takes to speed up a reaction. Now there's 4 factors that affect a reaction rate. There's the surface area, concentration, temperature, and a catalyst. Now, I want to see if you can see some common threads here. So for surface area, we're mostly talking about solids. So if we grind or crush up a solid, then we'll increase the surface area, and it increases the frequency of collisions. Now for the concentration, like an aqueous solution, we can just increase the concentration. I like to increase the molarity, so 12 molar versus 2 molar. And that will increase the collision just by the sheer number of particles available. Now temperature will also increase the chance of collisions having sufficient energy, right? Because we're also increasing the activation energy, right? But it will also increase the frequency of collisions because those particles are moving faster, they're going to collide more often. Now, for catalysts, that will lower the activation energy, so more molecules will have the sufficient activation energy. Now, important caveat is that a catalyst is not consumed in the reaction, so it will basically consume all of the reactants, or as many reactants as possible. Pretty cool, right? So for surface area, this cube right here only has 54 square inches. Inches. Who uses inches? And then the second one has 108, but the third one has 162 square inches. Just by splitting it up, they would all have the same mass, but by splitting them up, you are going to increase the surface area, therefore increase the amount of collisions possible. For the concentrated solutions, again, increasing the number of molecules in there. This would be something like a 12 molar solution versus the 2 molar solution, right? You have more molecules so they can collide more. And for temperature, you are seriously just going to speed them up. They hit each other more often, and therefore there will be more collisions. This is a good distribution of temperature right here. This would be the coldest one, and this would be the hottest one. And the coldest one is going to have its particle speed distribution. This is called the Maxwell-Boltzmann distribution. And what this is showing you is that even the hot ones have slow particles, but they also have extremely fast particles that will have a lot of energy to start a reaction. The cold ones didn't have that many fast molecules. So a catalyst I like to describe as a matchmaker, like from Mulan, or it's something that is going to participate in joining two atoms together, but it is going to be there. It's going to be necessary, but it's not actually going to participate in the relationship. So that's kind of like how I like to describe a catalyst. Now, what it will do in regards to an energy profile is it just shortens the hump. Now, sometimes you can actually see them do this kind of stuff where they'll make some kind of weird pathway right here. But again, the hump is smaller, so the activation energy is still, irregardless, lower. That is still kind of a weird little drawing there. So some people ask, what about volume? Well, yes. Volume will increase the rate of reaction, but only for gases. That is because you are also lower by reducing the volume. You will increase the pressure of the gases, which will increase the collisions. All right. So that only works for gases, not necessarily for solids or liquids. So just remember that the more collisions, the faster the reaction. That's basically how it is. Click on the YouTube link to check it out. It is a good little comparison to what that is. So this wraps up our heat unit, and this wraps up our kinetics. So I want y'all to have a great day and take it easy.